So we look at differentiable functions. Well, differentiable functions of several variables. Now, let's begin with the case when n is equal to 1. Even for this case, there is something new. So we are going to look at this function. Of one variable, x. Okay. And the graph is something like this. And we have the graph of the function, which is a curve. Okay. Then what do? We are going to fix a point. So we let A be in the domain of the function. So we have the point A here. Okay. Then we are going to impose an increment to this number A. So we let delta x. You may use small dx, which means the same thing. So I let delta x be an increment in A. which is usually very small. It may be positive, it may be negative. Okay. So it's like this. So it's A plus delta X. Okay. I am going to look at the point on the graph corresponding to the number A. And also the point on the graph corresponding to A plus delta X. So when there is a change in the value of A, there is a change in the corresponding value of Y. So this is the change along the x-axis, right? And this is the change in Y. This kind of geometric calculus is much more important than the epsilon delta calculus. Okay. Now, well, of course, epsilon delta calculus is also important in certain ways, especially in one variable. But it becomes less important when you go to higher dimensions. So this is an increment in A. Then what about the change in Y? Well, the change is here. So it's this point, which is f of A plus delta X. Okay, I mean the height here is f at A plus delta X, and the height here is the same as the height here, which is f of A. Right? So delta Y is f at A plus delta X. Minus f of A. Now, if you have a function, evaluate it at two endpoints, what are you tempted to do? Well, use the mean values here. Then by the mean value theorem, we can find a point C. Maybe I call that U. It doesn't matter. We can find a value U or a point U. And this point U is between A and A plus delta X. Okay. So let's say between A and A plus delta X. Something like this. And this value U enjoys the following property. So delta Y the change in Y. Calculus is about the studies of changes. So the change in Y is the same as F at A plus delta X. Minus F at A. But we don't want an expression like this. I want to express this change in terms of a derivative. Derivatives measure changes. So F prime at U times this point B, people call that B, minus A, which is delta X. Is that right? So we have this one. But we are not so much interested in the point U, because it's just some point in between A and A plus delta X. We don't know exactly where it is, but we for sure know that A is given to us at the beginning. So I want to compare F prime U and F prime A. All right? Now, again, in calculus, this delta something and this delta something, or the something and the something else are usually very small quantities. Okay. So I am going to look at epsilon. Which is f prime u minus f prime a. Okay, this epsilon is different from the epsilon in epsilon delta argument. This is just the distance between the derivative at u and the derivative at a. So, what can I do about this? Then this tells us that we are going to have the following thing. Therefore, the change in y, okay, is equal to f prime u, which is f prime a. Plus epsilon times delta x. Okay, we have this. Which is what? Therefore, the change in y is, let me write it here, f prime a plus epsilon, but I can multiply this delta x inside. Plus epsilon delta x. All right? All right. So we have something going like this. As I said before, delta x is very small. So a plus delta x is very close to a. So u is also very close to a because u is always in between. Okay? So delta x is very small, epsilon is very small, so the product is even smaller. So this is negligible. And then delta y is delta y over delta x, or dy over dx is the derivative at the point A. Okay, so delta y is given by this equation where this difference goes to 0 as delta x goes to 0. Okay. So this is the case for functions of one variable. Which is not what we are mostly interested in. But it serves as a motivation. Now I am going to look at n equal to 2. Okay. Which is becoming more interesting. So we are set. Be a function of two variables. So it's a function defined on some domain of the xy plane. Let's say B is a subset of R2. Okay. And we are going to look at its graph. Now, we let S be its graph. Okay. Which is a surface. In R3. It has two elements. Okay. To every point in the xy plane, there is a unique point in the surface. So this surface cannot curve like this. Okay. To each point, you have a unique point. Now, what are we going to do? We do similar things. So we let A be a point on the x-axis. want to write that. Okay. And I let B be a point in the y-axis. Okay. So let's say this is the point A. This is A. And then this is B. Okay. And these two numbers determine a point in the xy value. This is the point AB. And the point AB here has a point on the surface. Okay. So we have this one here. Now I am going to let delta x be an increment. In A. And we let delta y be an increment. In B. So I have a point here, which is A plus delta x. And a point here, which is B plus delta y. And these two numbers determine a point in the xy plane. So it's something like this. Right? So increments in A and B induce an increment in the point AB to this point. Then we are going to look at what happens to the change in Z. So we are going to look at delta Z.
Sir.
Yes.
So is A plus delta X and B plus delta Y also in the domain?
Yeah, because
Okay.
delta X and delta Y are very small.
Okay.
So they
I
are
think so.
close to AB. So I am going to have, sorry, I should draw this large. But that's okay. I should draw this large. But you understand what I mean. So this should come to this point. Or I can draw another one. Closer to this. Okay. So you see that this set would be changed like this. Right? So we have a change in the value of the function. And I am going to look at something like this. So this much here, which is very small, is delta Z. Right? And what is it? And then you see that is the value of the function f at this point minus the value of the function at this point. So delta Z is f at a plus delta x. B plus delta y minus f at AB. Right? From this picture. Now I don't need this. So delta z is equal to the difference of these two numbers, which I am going to write like this. Don't have enough space. And then I am going to introduce this number. But then I have to cancel it. And finally, I subtract f at AB. So these four terms will be simplified to these two terms.
Sir,
Yeah,
do you mind explaining why you did that, or will you explain it later?
we will see now.
Okay.
Right now. Now, if you look at the first two terms, keeping the second component constant, I can find a u between a and a plus delta x for which something happens. So we can find u between a and a plus delta x. Right? And a v between b and b plus delta 1. Such that the first term is the derivative of f, the partial derivative of f. And u, and then b plus delta y. Times delta x, right? I apply the mean value theorem to the first variable. And then I apply the mean value theorem to the second variable. So I have AV times delta y. Correct? Now I answer your question.
Yeah.
Yeah, good.
Sir, can you just explain where the delta x and the delta y come from?
Delta x comes from the difference between a plus delta x and a.
Oh, okay.
Okay, that's the mean value theorem. Now I am going to do the following thing. I let epsilon 1 to be the following thing is this derivative. I think there's a typo in my notes. Okay, yeah, there's a typo in my notes. So it's df dx and u b plus delta y okay. I just put u plus delta y in my notes. That's not correct. And then I have df dx ab. And epsilon 2 to be df dy av minus df dy ab. These two numbers are the important thing. Okay. Then what is delta x or delta z? Delta z is this big thing, and this big thing is just Let me put it elsewhere. So delta set is df dx ab plus epsilon 1. Right? Delta x. Plus this term here. Df dy av is df dy at ab plus epsilon 2 dy. All right? And we can simplify this a little bit. You will see later on, this is very important. Maybe not too soon. So is df dx at ab times delta x. Right? Plus df dy at ab times delta y plus epsilon 1 delta x plus epsilon 2 delta y. So it's similar to n equal 1. And epsilon 1, epsilon 2 go to 0. S delta x and delta y. Go to 0. Let me call this statement star because I don't want to write it down. Okay? Now, I make a definition. If the function of two variables satisfies this condition, star,
Sir, by the way, it's 1:22.
okay, give me 1 minute.
Okay.
Then we say that the function f is differentiable at AB. At AB. Okay, so I stop. You can do this for n variables, but then you have n partial derivatives. And then you have delta x1, delta x2, up to delta xn, epsilon 1, epsilon 2, up to epsilon n. I stop. And this df dx and df dy at AB is what people usually call the gradient of the function f. Okay. And the Greek letter for that is the so-called labyrinth. We shall come to that after your reading week. Now, questions.
So, sir, so just to clarify, the test is 13.1 to 13.3 and 14.3, right?
Yeah.
Okay.
Okay.
And the test is going to be very similar to the lecture examples and the WebAssign questions.
Well, I will make them very similar.
Okay.
Final judgment is on you.
Pardon me?
The final judgment is from you. You may say that it's not similar.
Huh.
Right?
Yeah.
But I will make it similar. And make
Okay.
it simple also. Don't worry.
Okay.
Okay?
And we should
And they should be easier than your WebAssign assignments.
Oh, okay.
Okay.
Okay. And sir, just to clarify, we should also be studying how to do the proofs that you've done in the lectures, right?
Yes.
Okay.
Okay. Simple proof. Well, maybe not this kind of proof.
Yeah. Okay, so simple proofs. Okay.
Yeah. Okay. Good.
And if we want like extra practice problems, we should do like the textbook questions that are similar to the WebAssign.
That's right.
Okay.
Actually, yesterday, some students asked me very difficult questions from WebAssign.
Yeah.
Yeah. So some of the problems there are actually quite difficult.
Yeah.
But you get help from WebAssign. Okay. And by the way,
And sir,
I have to say one more thing.
Okay.
Academic honesty is strictly enforced for all tests and the final examination.
Wait, sir, can you repeat that?
Academic honesty is strictly enforced.
Okay.
I
And sir-
allow you to consult with books, with notes, with the internet. Okay. But copying slavishly without understanding is not accepted. Collaborations with human beings, well, I mean peers, your peers, is also not allowed. And what's even worse is that you pose the problems to private tutoring companies. Okay.
Sir, so sometimes for the WebAssign questions, they tell us to use formulas that you didn't exactly put in the lectures. Do you also want us to know how to use these formulas and memorize what these formulas are?
You have to use your own judgment in it. I usually don't do that. I usually only give test questions based on something I have taught in class.
Okay.
But for WebAssign, it's good to practice a little bit more.
Yeah. Okay.
Okay.
All right.
Yeah.
All right. Thanks, sir. Have a good day.
You too.
Sir?
Yeah.
Can I ask how many questions will be on the test? Like
Well,
a range?
I have answered this question many times. 4 or 5, maybe.
Oh, okay. And then about the proof part, like I don't think you did a lot of proving
No.
in the lecture. So
Well, I consider this as proofs.
yeah, but kind of simple proofs, you know what I mean?
Well, for example, if you have, well, you still remember that that question? If you have a vector with constant length,
Yeah,
then
I do.
its derivative is perpendicular to the vector. Those
Yeah.
are the proofs, right?
Yeah, that one's from like lecture 2 or something. Lecture 2 or lecture 3.
Yeah, that one is on the lecture, but like other than that, I don't really see any other proofs.
Well, maybe I should increase the amount later on. Okay.
Thank you.
So this is why I tell you that this will be a simple test. Okay. There are not too many proofs, but there may be more after the reading week. Okay. So if there are no more questions, then that's it for today. Okay.
Hey, Professor.
Yeah.
I have it's not about a lecture this day. It's about assignment 2 because I have some problem with my VPN. Few days ago.
I saw the email. I will give you an extension. Okay.
Okay,
But
thanks.
I don't have time to do it yet.
Okay,
I
thanks.
think I have told you before that I have to go back to campus to teach in the morning, and then I have to come home to teach this calculus of several variables. And there are so many emails anyway.
Oh, okay, thanks.
Okay, all right, I will give you an extension.
Okay, thanks.
Oh, wait, so the extension is just for him or just for everyone?
Not for everyone, yeah, only
Oh.
for people with special reasoning,
Okay,
special rationale. Okay. Well, actually, I have given assignment 3. Not just assignment 2. And assignment 3 is due Friday. You need to do it for the test anyway. Is it okay? All right.